Welcome to this short introduction to the practical works in astrophysics at EPFL. So here is our teaching staff, so 8 faculty members who will train and supervise you during the semesters. We are working on 2 sites. One, of course, you know, is the EPFL campus. We are based at the Cubotron building, but we also work at Sauverny Observatory near Versoix, where we also have a small telescope, 60-centimeter telescope that we use sometimes depending on the weather and depending on the availability of staffs and students, that we use for some of the practical work that we propose. So practical works are spread over 2 semesters. The autumn semester, which is essentially coordinated by myself, and of course with assistants, postdocs, and PhD students, so we can interact with them. It's predefined practical work that illustrate a broad range of astrophysical phenomena. So prerequisites are simple: basic knowledge of astrophysics. So any course you have followed at EPFL or elsewhere on giving an introduction to astrophysics will be useful. Of course, if you know more, it's even better. Now, these practical works will introduce you to Python, the Python language that everybody uses now. It is quite spread. We'll use this to introduce you to image processing, how to carry out photometric measurements, so how to measure the brightness of astronomical objects on real CCD images. So we'll use real data from the Very Large Telescope in Chile, from the Hubble Space Telescope as well, and who knows, maybe from the new James Webb Space Telescope. We also introduce you to modeling of astrophysical phenomena. So for example, how to weight galaxies with rotation curves or with the velocity dispersions of stars in their center. And to do this, we do simple least square fitting of model and also Bayesian analysis using MCMC chains, for example. And of course, since large numerical simulations are widely used nowadays, you will be introduced on how to, maybe not how to do them, but how to manipulate them and how to interpret them and what's relevant in numerical simulations. The final report is really the final product, the thing you will get your grade on, and that should be written, of course, very clearly in English and as close as possible to a scientific paper. So of course, we will guide you in doing this. The key is to make clear and well-justified statements, produce useful and concise plots, in other words, be convincing, as you would do in a scientific paper. Then on the spring semester, you will work with any of our faculty, and that will be small individual research topics on which you will work for 1 day per week. The goal is a first contact with actual research, and the prerequisites are either the practical works you had on the first semester or any basic course on astrophysics. So the first semester practical work are not mandatory, but of course you will have to catch up with a number of things if you choose to do the spring semester practical works with us. And again, the final product is a report in English in the format of our scientific paper, again with good figures, good explanations, justify yourself, justify your choices, estimate your error bars. In other words, do science, do research. If you want to see examples of projects, go to this web page. So they're updated almost permanently, at least at the beginning of each semester, but sometimes more. So you can see some of the topics we are doing right now on this web page. Now, again, our scientific staff. So what we share is a broad range of techniques. Some of us use mostly observations, some of us do mostly theory, but some of us do also instrumentations to do observations, or even design instruments. Some of us do simulations, and many of us use machine learning to address some of our favorite astrophysical problems. Now, what are our favorite astrophysical problems? So it depends on each of us, although there are some connections, of course, between us. So Jean-Paul Kneib is doing observational cosmology. using gravitational lensing, the phenomenon of deviation of light by mass. He's also using galaxy surveys, knowing where galaxies are, how they cluster depending on their distance, so their redshift, and therefore how, depending on how the universe evolves. He's also, some of his work involves the development of instruments, and since more recently, the development or the Swiss contribution to the development of the Square Kilometre Array, a radio telescope that will be built, that is being built in South Africa and in Australia. Michaela Hirschmann is a new professor in the lab, in the group. She's studying galaxy formation and evolution, and in particular, how black holes in the center of galaxies influence their galaxy and vice versa. So in other words, how they co-evolve. She's also working on high redshift galaxies, so very distant galaxies that she can observe with Hubble Space Telescope, with James Webb now. And to do this, she's using mostly, but not only, of course, spectroscopy and numerical simulations to interpret the observations. On the more theoretical side, Jennifer Schober is interested in cosmological and magnetic fields. So very large-scale magnetic fields produced in the early universe, or even now, even in our Milky Way. So she's also studying astrophysical magnetic fields. So in other words, she's doing fluid dynamics with MHD, so magnetohydrodynamics turbulence. And she's much more versed on the theoretical side with help of numerical simulations. Emma Tolley is a data scientist. She's working with big data. She's doing machine learning. She's doing signal processing, mostly for radio astronomy in view of the Square Kilometre Array, but also in other areas of astrophysics and cosmology. Pascal Jablonka, who's doing galaxy formation and evolution, but this time more in light of the large-scale structures in the universe. So she's trying to see how individual galaxies or individual clusters of galaxies are influenced by the presence of cosmic filaments that are predicted in numerical simulations, or cosmic voids, areas where there are less galaxies, or next to clusters of galaxies. So in addition to that, she's doing near-field cosmology. So that's, in fact, trying to spot signatures of what happened in the early universe, when the universe was young. So signatures of what happened in the early universe in local objects. So when the universe is 13.7 billion years old. That's called near-field cosmology because, in fact, you're studying things locally, but you're doing cosmology about, you're trying to see what happened in the whole expansion of the universe from the Big Bang to now. And she's studying the first stars produced in the universe, the first galaxies, and all her work is about what happens in the local universe, but also in the distant universe. Richard Anderson, so he's our expert in variable objects in the universe, all of them, but mostly stars, variable stars, so stars that vary with time, so stars that pulsate. And stars that pulsate are very useful for two things. So first, to do stellar physics, because what happens on the surface of the stars when it pulsates gives you information of what happens in the center of the star. So therefore, you can study stellar physics by studying these stars. And they're also very useful because they have a known intrinsic luminosity. So if you know the intrinsic luminosity of an object and you know its observed luminosity, you know its distance. So Richard uses Cepheid stars, pulsating stars, in distant galaxies to measure the distance to the star and therefore to the galaxy where they reside. And this is directly linked to the Hubble constant, so the expansion rate of the universe currently observed, a problem that is really a hot topic at the moment. Yves Reva, also an expert in galaxy formation and evolution, but this time really on the side of the high performance computing. So he's really the one who develops the numerical simulations used by others in this group and beyond. So he's really our HPC expert, and he's producing numerical simulations, including what we call baryonic effects. So the impact of the physics of the gas and of the dust and even supernova explosions in galaxies. And finally, myself, I'm working on gravitational lensing. This can be used for many things. One thing is the measurement of the Hubble constant, like redshift, but with a completely different method. Since you can measure masses with gravitational lensing, you can also study dark matter. And since lensing is magnifying the light of the objects that it's affecting, you can also do quasar physics and use gravitational lensing as a, let's say, natural telescope to zoom in the central parts of galaxies where sometimes there is a quasar. And some of my research is also in pure signal processing, mostly image deconvolution, denoising, and other techniques. So thanks a lot for your attention. So we really looking forward to meeting you in person in the lab. Again, if you want to see examples of projects, you can go to our webpage. Thank you for your attention.